Alright guys, welcome back to circuits. If you haven't turned in your homework at this point, please just wait till the end. You're good, but from now on.
I like your shirt.
You like my shirt? Yeah, Zoom University. How many of you guys have attended Zoom University for the last 2 years? I'm a Zoom U alumni. Graduated in 2021. Yeah, so obviously we only lost like 7 minutes. That's not that bad. Definitely that stuff's important, so take care of your advanced standing once you finish all those courses. Does anybody have any questions before I get into some new material on the homework or last quiz? Questions, okay. We'll try and keep it to under 10 minutes so that I can spend the rest of the time on new stuff, all right? So what's your question?
It's mainly 1B.
1B? Okay, yeah. All right. So is that the one with the current source?
No, that's the one with the 2 voltages, but the other voltage,
that's 1C.
Oh, 1C.
So I made a video about that one, so I'm not going to spend a lot of time on it, but we'll take a glance at it. I don't want to spend too much time. Homework 6. This one?
Yeah.
So I don't know. How many saw my video on homework 1C?
I didn't realize you made a video.
Yeah, are you in the Google group?
I am.
Yeah, so we were messaging about it in the Google group. So I made a video solving this problem, or a very similar problem. Basically all mesh problems are really similar, you'll notice. Once you learn the proper way to make the loop equation, it's going to be the same thing every time, no matter how many loops there are, no matter what the sources are or aren't in the circuit. So if you had no problems with A, did you have any problems with A? If you had no problems with A, you shouldn't have had any problems with C. You basically, like I do, right, you start below the voltage source and make the loop equations. My guess would be some people have confusion when it comes to this middle resistor where the currents kind of coincide. Is that maybe a part of the problem? So what I'll do really quickly is I'll make the 2 equations for this one, and I'm not going to do any of the algebra, but I'll make the equations because I don't want to spend too much time on it. But let me just do the equations as if I were doing this problem. $6K, 4K, and 1K, 1 volt, 3 volts. Alright, so if I were going to make my little equations for this problem, do you have a preference for how I draw the currents? Clockwise, counterclockwise? Doesn't matter? Alright, so I'll do this one clockwise, and I'll also do this one clockwise. Fine? It's fine? So I call that I1 and this is I2. So I'm going to start at my voltage source because that's where I like to start, right? And I'm looking at, am I going up or down when I go across it, right? I'm going from a lower potential to a higher potential. So I'm going to write plus 3 volts because I'm going up. Then across this resistor, I'm dropping, and I'm dropping by I1 times 1K, right? And then across this resistor, I've got I1 flowing down, right? But I've got I2 flowing up. So I have to subtract them, right? I1 minus I2 times 6K. That's fine? So it's the other loop that caused problems with you?
Yeah.
Alright, so that's my first equation. So my second equation, I'm going to start again at the voltage source. It doesn't matter that it's not connected to ground. It's just a loop. Ground may as well not be there because the loop doesn't care about ground. It only cares about the drops in the circuit. So across this battery, I'm going up by 1 volt, right, in the direction that we're talking about. So I'm going to write plus 1 volt. And then across this 4K, I'm dropping by I2 times 4K, right? And then I get to this 6K, and I have I2 flowing up, and I have I1 flowing down. So I'm going to subtract I1 from I2. Okay?
So I think that it was the signs of I1.
You did I1 minus I2? Yeah, so if you're in this loop where I2 is flowing, you're looking in reference to I2. So the current flowing through the 6K in this case, on this side, would be whatever my I2 is minus whatever my I1 is. But if I'm on this side, it's my I1 minus whatever my I2 is. All right? So then from there, you just do the algebra. All right. Any other questions about this, or what were you guys'? I saw some questions over here. What were you guys' questions? It was this also?
So, just in case of clarification, so when I looked at this, I found that when you have both of the loops going in so they're both going clockwise in this case. So since they're both going clockwise, it would be subtraction. But if they were going, if one was going clockwise and the other one was going counterclockwise, it would be addition.
Yeah.
Okay, I was just saying, is that a good holistic view of okay, just in case you're what is wrong and you're oh wait, I'm adding what I'm supposed to be subtracting.
Yeah, basically you want to look at when the currents come together, are they going the same direction or are they going opposite directions? And when you have one going clockwise and the other going counterclockwise, then they kind of meet and flow through the resistor together, so you'd add them. But if they're countering each other, then you have to subtract them.
Great, thank you.
Yeah.
Technically, you can always set up your equations such that they always meet and flow through the resistor together, but you'll just get one of them to be negative, correct?
Yeah, exactly. You can always set it up however you want, right? That's why I always ask, does anybody have a preference? Because my preference is I like to have them add.
If you just always set it up to be double plus, then it's just easier because you'll just get a negative value later.
Yeah, and it's going to work out one way or another. So.
And you don't have to worry about the directions in that case, too.
Yeah, you never really have to worry about the direction. You could draw these going counterclockwise, clockwise. It doesn't make any difference. As long as you keep track of them, it's going to work. All right. Any other questions about this? Yeah. This one? Was this 6? This was 6. This was 6. This was 6.
It's because it's just 4 voltage dividers. 4 voltage dividers in parallel.
Yeah.
They all
So.
start at 12, and then they get halved.
So in every case here, yeah, this is a voltage divider, and what I want you guys to realize about this, that's good that you have that question. It means you did it right. But the point of this was to show you that it doesn't matter what the resistance is. It doesn't matter what the current is. What matters is the ratio of the resistors, right? If the resistors are equal, the voltage is half. So if it was 200K and 200K, this would still be 6 volts. You're just going to have a really low current flowing because in that branch, because there's a lot of resistance, right? So that's kind of what the purpose of this problem was, to show you that for all these different currents, you're going to get the exact same voltage at VV and at the exact same voltage at all these points, but very different currents, right? All right. Any other questions? And I'm going to move on to some new stuff. All right.
I think I might have forgotten to label VV in my homework. I had let a kid opt out for not saying that it was 12 volts.
I hope you don't, too. I can vouch for you if the grader asks me, but he probably won't ask me. All right, let's get into some new stuff. So I want to preface this by telling you all that when I took 220, the stuff I'm covering today, I thought was some of the hardest stuff. I don't necessarily think it's that hard now, but that's because I'm much further along. So if I'm going too fast or something's unclear to you, please stop me. Basically, what we're gonna go over a lot of new stuff today and probably next time, and I just want to make sure it's clear for you guys, much clearer for you than it was for me when I took the class. So the first thing I want to talk about is what is an electrical load, and some people may know what a load is. Basically, in electronics and anything having to do with circuitry, you usually have some power circuit that's going to be powering a load. Your load is what you're trying to power. So somebody said it could be a light bulb, it could be an LED, it could be some other integrated circuit that we need to provide power to. Basically, anything that's going to consume power is known as a load. Okay? So I don't know how many of you guys remember me talking about the voltage divider, right? When we did the voltage divider, I kind of talked about it as if it were a system, and I called this the input of the system. And then if I have, my divider set up in like the standard form, this is the output of the system, right? I called that V in and V out. So let's just take this as a mini system, right? Where I have, what's in this circuit is going to be like my box. That's going to be like my system. And it just has an input, V in, and it has an output, V out, right? So what's inside of here is a voltage divider. So let's say that the voltage divider was my circuit, right? Also, don't freak out about this stuff and don't worry too much about taking notes, because I'm just using this to preface what I'm actually going to talk about today. I want you to have some background about what a load is. Okay? So say my voltage divider was my system, and I wanted to use that voltage divider system to power an LED or something, right? So I would connect an LED out here. That's what an LED looks like if you were to look at the symbol. It's a diode with a couple arrows to show that there's light being emitted. And then we'll just connect a resistor to limit the current. So right here, this circuit right here, this would be my load. And you judge how big or small a load is based on how much current it pulls, okay? So that's another thing that confused me when I took the class. Dr. Baker would talk about big loads and small loads, and he'd say, like, a 2 ohm resistor is a really big load, and that didn't make any sense to me because that doesn't sound like a big load, right? That sounds like a small load. But what we judge a load based on is how much current it pulls, how much current is being drawn by the load, okay? So I'm just going to write that. We basically care about how much current flows through the load.
So a lower resistance is a higher load.
Exactly. A higher resistance, like a really large resistor, would be a very small load because not a lot of current's going to flow through it. And another thing, you're very rarely going to see a resistor as a load. We'll use resistors to model loads, but you're not going to. It wouldn't make much sense to build a circuit to power a resistor, right? A load is basically something you're trying to power. So you might try and power an LED, you might try and power a light bulb. Very rarely you're going to just be trying to power a resistor. But we do use resistors to model loads, okay? So moving forward and into what we're going to talk about today, we're going to see that resistors are going to be used as our load, but it's just modeling what a real load would be, which may be a light bulb. It could be any number of things that draws power, okay? For example, if you're, tapping power off from the grid would be your giant system, and you're trying to power your refrigerator. Your refrigerator is the load for the grid. It's part of the load. The grid has a huge load. It has to power a whole bunch of stuff. But anything that it's trying to power is part of the load. Okay? That's a really high-level view of what a load is. I just wanted to kind of talk about it so that you're not, I don't use the word load now and you're like, what in the world is he talking about? Because that's what Dr. Baker did when I took the class, and I had no idea what he was talking about. So at least you have an idea what I'm talking about. I'm not going to quiz you on this. I am going to quiz you on the stuff that we're doing next, but I just want you to know like a little bit about what a load is. So now, without any further delay, I'm going to move on to the new stuff. And basically, the new stuff is called Thevenin and Norton equivalent circuits. And I'm going to write that up top. Okay. So basically, Thevenin and Norton are some guys who came up with this theorem. Well, they have their own theorems, but they're very related. Basically, Thevenin's theorem states that any circuit, no matter how complicated, as long as the equations that govern the circuit are all linear, which is everything we've seen so far, right? We haven't had any quadratics, we haven't had any exponents, we haven't had any logarithms, nothing like that. Any circuit that has linear equations, it's called a linear circuit. It can basically be broken down into an equivalent circuit that's made up of just a voltage source in series with a resistor. Okay? So Thevenin's theorem is that any linear circuit can basically be replaced by a voltage source in series with a resistor. Just like this. Any circuit, doesn't matter how complicated, as long as its equations are linear, it can be replaced by this right here. And this voltage source will be known as the Thevenin voltage, and this resistor will be known as the Thevenin resistance. Okay? And so obviously what we're going to go through today, and probably a little bit next time, is how to find those equivalents, how to break a circuit down to where we just get this little equivalent circuit. And basically, I think it would be fair if I said some of the circuits you've seen so far are much more complicated than this, right? This was some of the first stuff we saw. So if we can break a circuit down into just this, it's going to become much easier for us to solve very quickly. So the purpose of this, the whole reason why they wanted to come up with this theorem is because it allows you to test a bunch of different loads, right? Imagine I had a circuit like, let's just say, like this one, and then I wanted to say that R5 was my load. Say I was trying to power R5. That's what I was trying to do here. And I want to know if I tried different values of resistance at R5, what would VB be, right? What would it be? What would be the voltage at VB? Well, every time you change, also this was before they had LT Spice where you can just run a bunch of simulations really quickly. But if I want to find different values of VB, I'm going to have to do mesh or superposition every single time, and that's going to be horrible, right? That's ridiculous. So if I could break this circuit down to where all it is this, and then I connect that resistor here, I can get the exact same result, the same voltage, the same current, using this equivalent circuit. So that's the purpose of these equivalents, is that it makes it really easy to calculate the voltage at this node, say, over a bunch of different load resistances, okay? So that's Thevenin's theorem. Any linear circuit can be replaced by a voltage source in series with a resistor, okay? No matter how complicated. Norton has a very similar theorem. He says any linear circuit can be replaced by a current source in parallel with a resistor. Okay? And now this is going to be called my Norton current, and this will be called my Norton resistance. Okay? So basically, if I take a circuit, any linear circuit, it will have a Thevenin equivalent and it will have a Norton equivalent. Okay? And one thing that's interesting is that the Thevenin resistance and the Norton resistance are always equal to each other. Okay? So if you find the Thevenin and the Norton equivalents and you get two different resistance values, then you did something wrong. So I'm going to write that R Thevenin is always equal to R Norton. Okay. So now that I've gotten that out of the way, I want to do a quick example and show you what I mean. So let's say I take a little circuit. Let's go with a voltage source, resistor, 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 and then one more resistor. And let's say that this is my load. This resistor right here is my load. So I'm basically using this rest of this circuitry to try and power this load resistor, right? Well, I want to test a bunch of different load values, and I don't want to have to do mesh or any, like, you know, series resistance here and then a parallel and blah, 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 all the old stuff. We don't want to do all that, right? So instead, I'm just going to find a Thevenin and a Norton equivalent for this circuit, and then we could, if we wanted to, we could try a bunch of different loads really quickly. We're not going to do that. But I'm going to go through the process of making the equivalent circuit. So let's say my load's a 1K resistor. Also, guys, it's very, what do you call it when something's like methodical? Like it's a very, there's a mechanism to solving these problems step by step. So I'm going to list the steps, and you just need to make sure that you know how to follow each of the steps, okay? And I'm going to do them, obviously. I'm going to show you. But so step one is going to be to find the Thevenin voltage. And how do we do that? No, it's not just the voltage. It might be, but it's not. It's not necessarily. So what you're going to do to find the Thevenin voltage is you're going to remove the load resistor. You're going to take it out of the circuit, okay? So what you're left with in that case is a voltage source, resistor, 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 and then there's nothing here, right? That's open now. There's nothing there. And so imagine I still had ground here. What you need to do is you need to find the voltage between these 2 points, where I removed the resistor. Whatever that voltage is going to be my Thevenin voltage, okay? So I've still got a 5 volt here, a 1K, I've got a 3K, and I've got a 2K. All right? You'll notice that my 3K isn't going to have any current flowing through it because it's not connected anywhere, right? So I can basically get rid of my 3K. Everybody cool with that? No current's going to flow. So whatever this voltage is going to be equal to this voltage. So it's basically just a wire. I can get rid of the 3K. So whatever this voltage is right here is going to be the same as whatever this voltage is right here. And that's just a voltage divider, right? So my V Thevenin basically is equal to 5 volts times 2K over 1K plus 2K, right? And that's going to be what's 2/3 of 5? I don't know, 3 point something? 3.1667? I don't know. I'll do it. Nice. 3.33 volts. So what I'm doing right now is I'm finding a Thevenin equivalent, right? Because I found my Thevenin voltage. So now what I need to do is I need to find my Thevenin resistance. Because I found my Thevenin voltage, right? Now all I need to do is find my Thevenin resistance. So how do you find the Thevenin resistance? That's the second thing. Thevenin resistance. And so do you guys remember how similarly, it's going to be very similar to what we did in superposition. When you're trying to get rid of a voltage source, you're going to short across the voltage source. And when you're trying to get rid of a current source, you're going to open up where the current source was. So to find the Thevenin resistance, you basically get rid of all the power sources, and then you calculate the resistance between the two terminals of the load resistor that we removed. Okay? So if I was going to draw this without the battery, right, it would be a short to ground. And then I'd have a 1K, I'd have a 2K, and I'd have a 3K.
Can you pick any one of those resistors to be your load resistor, or is there a reason that you picked a 1K on the outside of the circuit?
So this is just an example, so I just said that would be my load. It could have been any one of these resistors, in which case, so say at the beginning I said that the 3K was my load, that'd be the resistor that you remove.
Okay.
Okay.
Yeah, so you can just pick whichever one you want and go from there.
Mm-hmm.
Got it.
So now, what we need to do is we need to find the resistance between our two terminals. So I have one terminal here and I have another terminal at ground, right? Well, these are all at ground. So I'm basically, if I was going to look into the circuit, I need to see how much resistance do I basically have to go through in order to get to the other terminal, okay? So if I'm starting here, I definitely have a 3K, and then I see a 1K and a 2K in parallel, right? You guys see that these two are in parallel? They share this node, and they also share ground, okay? So the 1K and the 2K are in parallel, so I need to combine those, right? 1K in parallel with 2K is equal to 1K times 2K over 1K plus 2K. I don't know, what is that? 667 ohms?
Yeah.
Okay. So now I know then that these could be replaced by a 667 ohm, and that's in series with my 3K, right? Everybody good with that? So then my total resistance, my R Thevenin, is 3.667K. Okay? So now I found my Thevenin voltage, I found my Thevenin resistance. That means that I could replace all this circuitry, right, except for the load, with basically this, right, this circuit right here. So my resulting circuit would be a 3.33 volt voltage source in series with a, 3.667K resistor. And now I could plug my load back in and I would get the exact same calculations that I would have gotten with the original circuit. So that's why this is important. Obviously it doesn't seem, this might seem like too much work for a circuit this simple, but the purpose for this technique is for much, much more complicated circuits. So I think you ought to be happy that I'm not going to give you much, much more complicated circuits to do this with. But just know that the purpose was for very complicated circuits to test different loads. And now we could do that. So basically, we had a 1K load. We could plug the 1K back in here. And what I'm saying is that whatever this original output voltage would have been, V out right here, say the voltage here was V out, that will be the same as this voltage now for that same load. So I could change this to a 500 ohm resistor, and that voltage would be the same as this voltage. So now we're checking what would my voltage be in this circuit, but we're using this equivalent circuit. Okay, so this is my Thevenin equivalent. All right. So let's move on to another page, and I'll do show you how to find the Norton equivalent. Finding the Norton resistance is exactly the same, right? The Norton and the Thevenin resistors are exactly the same. So you do the same exact thing to find the Norton resistance. But finding the Norton current, there's a little bit something different that we're going to have to do, and we'll do that now. So let me go to a new page. I want to redraw this circuit, but I guess I'm going to have to. So this was my circuit. This is my 1K load. And then I had 3K, 2K, 1K, 5 volts. So now I want to find the Norton equivalent. So the first thing I'm going to do is find my Norton current. And how do I do that? Well, previously we wanted to find the Thevenin voltage. What we did was we removed the load, right? I removed it, and then I found the voltage between the 2 points where I removed the resistor from, right? So now what we're going to do is we're going to remove the load, and we're going to put a wire there, and we're going to measure the current through that wire. And that's my Norton current, basically. Okay? So again, let me change colors. So I've got my original circuit, a 5 volt, a 1K, a 2K, 3K, and then I would have had a resistor right there, but I removed it, right? That's gone. That's my load. Okay, and so what I said is you're going to put a short right here. You're going to put a wire, and then we're going to measure the current that flows through that wire. All right? So basically, in this case, what you'd have to do is you'd have to, go through the process of taking the 3K and the 2K in parallel, which we'll do real quick. What's 3K parallel with 2K? What is it? I got 1.2. It's 1.2? I realized that, yeah, it's not worth it. I don't remember what I realized, sorry. I think it's like this if you have a value that's like 1.5 times the size of the smaller one, then the equivalent is always 60% of the smaller one. I realized that somehow. I don't know how. So if you had like 12K and 18K, right? That's 18K is 1.5 times bigger than 12K, then the equivalent would be 60% of 12K, whatever that is. I don't know how. I think that works out though, because this is 60% of this. So just in case you remember that ridiculously freakish fact, it might help you. All right, so now what we're left with basically is a 1K and a 1.2K, right? And what we're trying to do, we're trying to find the current that was flowing through this 3K. And we first need to find what this voltage would have been in order to find out what that 3K was. So I guess this is just 5 times 1.2 over 2.2, whatever that is. That's 2.727, so that's my voltage here. And so now I know that that was my voltage here, right? That was going to be my voltage there. And so I can go 2.727 minus 0 over 3K, and that'll give me my current through that short that I created, right? So whatever, what did I say? This was 2.727 volts. So I divide that by 3K, and that will give me my Norton current. And that is 0.909 milliamps. That's I Norton. So I know my I Norton. I already found our Thevenin earlier. That's equal to R Norton, and that's 3.667 K. Right? And so I can basically say that this circuitry, right, the same circuitry that we just Thevenized. So when you do this process, it's called Thevenizing, and when you do this process, it's called Nortonizing. It's kind of weird, but that's what they call it. So my Norton equivalent would look like a current source of 0.909 milliamps in parallel with a 3.667 K resistor, and then my load of 1K could basically be put right there. And now I would get the same V out here that I got there, that I got over here. Okay, so I know that was a lot. I'm not even going to pretend like it wasn't. So we still have like 22 minutes. I'm probably doing another example, but does anybody have any questions?
Oh, could you put that one back up?
This one?
Yeah, I'm still covering stuff, sorry.
Yeah. Any questions? Yeah.
Oh, sorry, no,
Slow down, James. Slow down. You're going too fast for my comprehension.
I mean, yeah, I know I'm going fast.
I mean, I would have to watch this video again.
Yeah, that's good. You should have to watch it again. That's why I record them.
Thank you.
But I will go through it again slower. Does anybody have any questions about the explanation? Like, what the heck are you talking about, dude? What is an equivalent circuit? What's the point? What's up?
So we have to use both processes to find the equivalent circuit?
No, so you don't have to use both processes. You can use either or, but I'm going to ask you to use both on the homework so that you know how to do both. But basically, so say I had this initial circuit, right? I want to just explain it on a high level. This right here is some circuit. It's going to have this 1K load resistance, and I have a voltage across that resistance, right? Well, let's say I'm a design engineer, and I want to check if I change that load resistance, how does my output voltage change, right? And I don't want to go through the process every time of saying, okay, first I have to combine my load with this 3K in series, then I have to combine that series resistance with this 2K in parallel, and then I do the voltage divider, and then I got to work backwards. You don't want to do all that. That's ridiculous. I would rather just plug my load in here and I just have a voltage divider. That's the purpose, is so that you can try a bunch of different load resistors here out here. You can basically try them, and you'll get the same value for V out with either one of these equivalents that you would have if you had the original circuit in there. But you don't have to go through all the crazy analysis of finding that V out. You can just do a quick voltage divider or a quick current divider. Does that make sense? That's the purpose of this. So basically, like I said, right, this is going to be a lot. We're going to go over it today. We're going to go over it Wednesday. I'll do another example. But does anybody have any questions now about the theory behind it or about what the purpose of the equivalent circuits is? Yes?
I see the other page real quick.
Yeah. I mean, I scan all the notes, but... So basically what I have now is I have this Norton equivalent, right? I have the Thevenin equivalent. Both of those are equivalent circuits for this original circuit. And if I plug in the 1K load to any of those circuits, I should get the same value of V out, right? That's what's happening here. So I think on the next homework, am I good? Here, one sec. On the next homework, I put a couple, just two of these, very similar, down here. You need to Thevenize, Nortonize, blah, blah, blah. So basically, let's just look at this one. So if you were going to do this problem for homework, what you need to do is you first need to remove, well, actually no. The first thing you need to do is calculate V out, because you want to use that as your reference, right? So you're going to calculate V out using whatever method you'd like that you've done so far. You could combine these two in parallel and then do a voltage divider. You could do whatever you'd like. Now you have that V out. Now what you're going to do is you're going to replace all this circuitry to the left of the red dots with a Thevenin and a Norton equivalent. And then you're going to plug the load resistor back into those equivalents that you just found. And you should get the same value for V out. Okay? Does that make sense? So you're basically, and like I said, it's not going to seem like it makes any sense. You're like, why am I replacing this little amount of circuitry? The whole purpose of this is for big circuits, but I don't want to give you guys crazy circuits. Okay? So, and the same thing over here. What am I doing? All right. Same thing over here. You remove this 2K resistor, and you go ahead and you first find V out with the 2K in there. And then you're going to remove the 2K, you're going to Thevenize the circuit, you're going to Nortonize the circuit, and then you plug the 2K back into your equivalents and check that it matches your initial value of V out. So that's, the instructions say that, I'm saying it, but I know it's probably still very foggy, so I'll do a very similar example. I just did a very similar example, but I'll do another similar example. Let's use a current source this time, so I'll do something similar to this. Any questions before I do another example? All right, what do I got? I got like 17 minutes before I give the quiz. Quiz is not on this. Quiz is from your previous homework, so don't freak out. Okay. So don't worry, I'm just copying down a similar problem. So let's say I want to do it 1 milliamp, 2K, 1K, and all right, so let's say that this is my circuit. And I want to find basically Thevenin and Norton equivalents for the circuitry to the left of the 3K resistor. Let's say that the 3K resistor is my load. I'm trying to power this 3K resistor. So first, I'll do Thevenin. I'll do Thevenin first. Actually, sorry. First, I'm going to find what V out is actually supposed to be. Without doing a bunch of crazy work, would everyone agree that I could just take the 3K and the 1K in parallel and then find the voltage across that equivalent, and that would give me V out? Okay, so I'm going to do that without writing anything down. So it's 750 ohms times 1 milliamp, which would give me basically 0.75 volts. So that's my voltage that I'm looking to get. I should get that same voltage when I find my equivalents and I plug in my load. So this is my load, 3K. So first I'll do Thevenin. And when I do Thevenin, I'm looking for a Thevenin voltage and I'm looking for a Thevenin resistance. Right, Ryan? Right, Ryan?
Sorry.
It's all good. Okay, so 2K, 1K. I remove the resistor, right? I've got 1K there, and I've got 2K there, and I'm trying to find the voltage between these 2 points. All right? That's going to be my Thevenin voltage. So some people call it VOC, V open circuit. So it's like an open circuit wherever I remove the resistor, but it's basically just my Thevenin voltage. I'm also going to split these so that I can do Norton on the other side. So whatever that voltage is my Thevenin voltage, right? Okay, so I have 1 milliamp flowing in this loop, and would everyone just agree that 1 milliamp times 1K gives me 1 volt right here? So that's my open circuit voltage. That's my Thevenin voltage. Good? So now, for my Thevenin equivalent, I basically have the voltage done already. It's 1 volt. And now I need to find out what this value of this the Thevenin resistor is going to be. So this is my Thevenin equivalent circuit. And then, like I said, I'm going to plug the 3K load back in over here. And then I should get the same value for V out. So what we're looking for is my Thevenin resistance now. And what did I say about the Thevenin resistance? Basically what we need to do is we short all our batteries, we open all our current sources, and then we measure the resistance between the 2 points, right? So that was to find my Thevenin voltage. Now I just removed this current source, so that's not there anymore. I've got 2K here. I've got 1K here. And I'm trying to find the resistance between this point and this point. So like I said, I'm going to send a current in here, and basically how much resistance does it have to go through in order to get to the other side is kind of what I'm looking at. And basically it can't go through the 2K, so the only thing it can go through is the 1K. Right? Everyone agree? So I go ahead and I say our Thevenin is equal to 1K. Let me just write that too. So I write 1K right here. And now my Thevenin equivalent is done. My Thevenin equivalent is done. And what I should see is that my V out should be exactly equal to my V out from my original circuit when I put this load back in. So some of you may have already noticed that it will be, but it's just a voltage divider. It's going to be 1 times 3 over 4, which gives me 0.75 volts. So I can confirm that that equivalent is correct. Any questions about that before I do anything with Norton? Any questions about anything I did? Yeah.
Why can't the current pass through the loop?
There's nowhere for it to flow. So current needs a loop, basically. It needs a path. It would basically try to go through the 2K, and it wouldn't be able to go anywhere.
Oh, yeah.
So this open has 0 current flowing through it. Anytime you see an open, there's no current flowing through that entire branch. So if I put 10 resistors in a string and then I open one of them up, there's going to be no current flowing through any of them. Right? Other questions? I saw another hand. Yeah.
I was just wondering, and again, the point of this is to, if we just change the load resistance, we just want to see like what it's going to be, like how much current it's going to draw, what its voltage will be, stuff like that.
Right. So basically, if I took out this 3K and replaced it with a 1K, this V out would change, right? This V out is going to change exactly the same. So it's used to test different loads without having to and again, right, we're living in the 21st century where we have LT Spice and we could just run a sweep simulation where we do a bunch of resistances. They didn't have this. So the whole purpose of this was to do a bunch of calculations really, really quickly, and they like voltage dividers. So, well, Thevenin did. I guess Norton liked current dividers. I don't know. All right, so I got my Thevenin circuit. I got the right V out. Right? This V out matches that V out. That means I did it right. Now I'm going to do my Norton equivalent. And so, like I said, our Thevenin and our Norton are the same. So I've already got that. However I found that, that's going to work for both of them. Okay? So I'm going to come over here, and this is going to, I don't want to move anything. So Norton, let's say. Okay, I got about 10 minutes. My Norton equivalent is going to be a current source, right? My Norton current, which we haven't found yet, in parallel with my Norton resistance, which I know already, right? It's 1K. And then I connect my load, my 3K, and I should get the same voltage V out here that I got over here. So basically I already know my R Norton. This is my load. And I need to find my Norton current, right? And how do I find it? Well, what I do is I short across the terminals where I removed the load, and I find the current through those terminals. Okay, so my original circuit looked something like this. I had a 1 milliamp, I have a 2K, I have a 1K, and then out here I had a 3K, but I'm replacing it with a short circuit. Right? There's a wire there now. 0 resistance. It's just a wire. Okay? So that's 1K, this is 2K, and I want to measure the current flowing through there. Basically, my current's going to flow through this 2K, and then it's going to see 2 paths, right? It's going to see the path with absolutely no resistance, and it's going to see the path with resistance, and it's only going to go through the path with no resistance. So all of the current flows basically around that 1K. None of it will flow through the 1K. Another way you can see it is that I just shorted both sides of the 1K to ground, right? So both sides are at the same voltage, which means no current will flow through it, right? Does everybody see that? I have 0 volts here, I have 0 volts here. So current will flow through the 2K because I don't have 0 volts here, I have some voltage here, we don't know what it is. But I know that my 1 milliamp is flowing through that 2K, but it will not flow through this 1K because both sides of the 1K are the same voltage. Is that clear? Right? My I equals V over R, my V is 0, so my I is 0. Alright, so basically the current through here was my, whatever my I Norton is, and that's going to be 1 milliamp. The whole 1 milliamp is going to flow through there. So that means this is 1 milliamp. Okay? And so now, if I go over here, I have 1 milliamp flowing, and basically it's going to be a current divider. If I do the current divider, I should get that V out is going to be equal to 0.75 volts, right? So here, let me just make another little area for me to do some work. My I total is equal to 1 milliamp, right? And then if I want to find I through the 1K, let's say, my current, let's say through the 1K, is equal to the total, which is 1 milliamp, times 3K over 4K, right? This is just the current divider. So it's going to be 0.75 milliamps. That's the current through my 1K. Got that? And now if I take that current that's through my 1K and I go 0.75 milliamps times 1K, then I get V out, which is 0.75 volts, right? So I just confirm that the output of my Norton equivalent is equal to the output of my original circuit is equal to the output of my Thevenin equivalent. Questions? Anything at all that's confusing you? We could even just talk about it. We have like 5 minutes. I want to use the 5 minutes. We can even just talk about whatever about this is bothering you. Yeah.
So you said there's no current flowing through the 1K resistor?
That's right.
It's just going through the wire. So why are you calculating 1 milliamp times 3 over 4K?
Okay, so this is going back to the original circuit.
Oh,
So that's why I made another box. So this right here is work for that circuit. I was going back to the original to prove that my V out for that Norton, sorry, this isn't the original circuit, this is the Norton equivalent circuit with my load plugged back in. So this is my original, right? Then this is my Thevenin equivalent, and then this is my Norton equivalent. And so I wanted to show that I ran out of room up here basically, and I just wanted to do a little bit of work to show that my output was equal to the original output. Right? What's up?
So similar to superposition, when you're doing Thevenin, when trying to basically create a voltage divider, you would just like take out that entire the entire load itself. But then when you're trying to find the current or the Norton, you would just you would make it a line, similar to the way that you do in superposition.
So basically, there's a couple of things going on here. So let me go to a new page, and I'll write some basic rules down. And I'm also going to give you guys a link. There's this thing called All About Circuits. I don't know if anyone's seen it online. They do a really good job explaining Thevenin and Norton. They have example problems. They have it written out why they came up with it. That's where I got all my research for how to give you guys the presentation of why this is even necessary. But I'll post that link on the webpage so that everyone can use it. because I think it's really helpful. But basically, there's a couple different things going on here. There are 3 things you're trying to find. There's the Thevenin voltage, the Norton current, and then that resistor that's used for both cases, right? So right now, I'm basically going to write out what it is that you have to do when you're trying to find those things. So when you're trying to find, so I'm going to say like when finding do blah, 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 blah. Okay? So when you're trying to find the Thevenin voltage, what you want to do is you want to find the voltage across the load terminals. And that voltage is your Thevenin voltage. So you basically remove the load resistance from the original circuit and you find the voltage that's there once that resistor is gone.
Yeah, I'm saying like similar to the way that you would remove the current source when finding resistor.
Yeah. But also when you're trying to find the Thevenin resistance, you have to keep track of, is it a voltage source that I'm removing? Because if it's a voltage source, I short. Is it a current source I'm removing? If it's a current source, I open.
Right.
And if it's a resistor, then yes, you open. If that's what you're asking.
Yeah.
Yeah, you open. So when you pull the resistor out, you basically, like I did here, you know what, let me just draw it. So say I had, I don't know, some circuit, and then I have, you know, my resistor, my load is connected like this. You basically, as if you were literally pulling it out.
Right.
And so what you'd be left with is the same circuit, but literally nothing there.
Right. Makes sense.
You're not going to draw a wire, if that's what you're asking, right?
Yeah, but then I was saying with the Norton, do you drill that wire?
No.
No.
So when you're pulling, see, this is why it depends on what you're trying to find.
Right.
If you're pulling out the resistor, in either case, oh, okay, I know what you mean. What you mean. Because when you pull out the resistor for the Norton equivalent, you do draw a wire here because you're trying to find the current through it.
Yeah, that's what I'm saying.
And when you're trying to find the Thevenin voltage, you don't draw a wire here because you're trying to find the voltage.
Right.
So yes.
Yeah.
So yeah, you got it. Yeah.
I was just wondering, can't you just find the voltage drop across the resistor?
Hold on. What do you mean?
I mean, so if we're finding our Thevenin voltage, we're finding the voltage across the load terminals as though we just removed the resistor, right? But you could also, if the resistor, the load resistor is connected to ground, and we're lucky enough to have that happen, then the voltage drop across the resistor will just be what we're looking for.
No. And the reason is, when I have this 3K here, the equivalent resistance here is something smaller than 1K. When I pull it out, it's 1K. Right?
Oh, okay.
So the voltage drop across this 3K is not going to be the same as the open circuit voltage when I don't have the 3K there.
Okay.
So you have to pull it out, or you won't do it right. Does everybody understand his question?
Yeah.
Basically, he's asking, could I just leave the 3K in here and solve the voltage across it? You can't. You have to pull it out because that V out, right, that's not going to be the same as this voltage. We just proved that. V out with it in there was 0.75. Without it, it was 1 volt. Right? So it's not going to be the same. Any other questions? Here, let me finish this real quick. So when you find the Thevenin voltage, you find the voltage across the load terminals, and that's with load resistor removed. And it's going to be an open. When I find my Norton current, I am trying to find the current through the load terminals with load resistor removed, but it's a short, right? It's not going to be an open like this. So this was a voltage. Over here, this is my circuit. I've got my load, right? I pull it out. And now what I have is a short. And then the current is the Norton current, right? Basically my current flowing down through there. And then last but not least is my Thevenin resistance. Thevenin Norton resistance. And what I do is I basically get rid of all power sources, and that means short across voltage sources, open current sources, and then I find the resistance between the two load terminals. So basically my examples, I did those three things, but obviously this is just a written out version. So if this is my circuit, and I have my resistor, I basically no longer have that resistor in there. And I look, if I were to send a current in here, and it had to go through the circuit and come out here, how much resistance does it have to go through, basically? You want to find whatever that equivalent is, okay? And that, whatever that total resistance is going to be your Thevenin or your Norton resistance, okay? All right, that's it for that stuff today. We'll definitely go over more of it next time. I know it's probably really overwhelming. There's two simple problems on the homework. If you have problems with them, definitely come to my office or reach out through the group. That's it for today, and now I'm going to give you guys a quiz. Do you want to take it today or in my office?
No, I'll take it in your office.
All right, sounds good.